see. I didn't expect so many people to join shortly before Christmas. I thought you were all already traveling. So today we have a little extra lecture. It's not only Christmas, but it's also the lecture where we finally got to do some calculations, some renormalization calculations. And because this is a lecture focused on calculations, it's a kind of little bit of an add-on lecture. So we have the intuitive stuff we did last time, and now we see how it works in practice, but you don't need this lecture actually for the remainder of this course. So let me share the screen. So you see before I switch off the video, so you see that I brought a little pyramid here. It's one of the traditional things that is produced in the mountains around Dresden. And that's what a lot of people now have in their windows or in their apartments. And so a lot of the Christmas traditions in Germany actually come from this area here around Dresden. And so let's move on, and let me give you a little reminder. Share the screen. There we go. Let's start with a little reminder. There we go. Yeah, so you've seen that already now many times. For some reason, it took us an entire lecture to just define this model. And so this is the epidemic model we want to treat analytically today. As this epidemic model consists of two kinds of people: the infected ones, the susceptible ones, and then we put these people on a lattice in the world, and when these infected people can infect susceptible ones or non-infected people if they are on the neighboring lattice side. And then infected people can also recover and turn into susceptible or non-infected people. So this is the little model that we introduced, and I also just a quick reminder that this model produces critical behavior. That means that we have a value where we balance the interaction and recovery rates in a certain way, where there's a sort of balance between infection and recovery. And if we tune these parameters to be in this state, then we get these self-similar states that you see in the middle, where both the spatial correlation length, but also the temporal correlation length is infinite. Yeah. Then we moved on, and we inferred the field theory description of this SI model. Yeah, and the field theory description, the Martin-Citrer-Rose functional integral is here on the top. Now that's the Martin-Citrer-Rose, the generating functional. And you can see here, we essentially have an Engendré equation. And then we get these additional terms here. That's because we have effective interactions between lattice sites and multiplicative noise. That means that the noise itself depends on the strength of these fields, on the concentration of these individuals. Now the functional integrals has two kinds of fields. Now the phi field, which is the density of infected people, but we also have the phi tilde field, which is the response field. A couple of lectures ago, we discussed that this describes the instantaneous response of our field to very small perturbations. That's the intuition about this response field. Yeah, and we get this response field because we don't have the noise explicitly here anymore. So the response field in some way mimics the noise. Yeah. So we can write this functional, generating functional by separating the action into two parts. Yeah, a free part, so that we call that free part, because in this free part we have terms that are quadratic in the fields. Yeah, so this is the Gaussian part that we could integrate if we want. Now, this is this first part here, that's quadratic. And then we have terms that have higher order interactions between the fields. Yeah, phi squared times phi tilde, and so on. Yeah, and these we call the interaction part. And we treat this interaction part. The first part is essentially Gaussian. So we have second order in the fields. And we can help that we can deal with that. But the other parts are non-Gaussian. So we have higher orders in these fields, and we don't know how to perform integrals around this last interacting part. So we separate these two. And if we separate these two and we do some rescaling, yeah, of these parameters to make things look simple, we get to this form where the free part is given as usual, yeah, and the interacting part now has a more compact form that we also already derived 2 lectures ago. Now we can transform this to Fourier space, and in this Fourier space, the spatial derivatives, like this one here, become algebraic quantities. So the wave vector squared here represents diffusion, and here the omega, I omega, is what we get from the time derivative. And then we have here these interaction terms that you look at as complex as usual. So now we want to understand the critical behavior of this model. That means what we want to understand is the macroscopic behavior of macroscopic quantities in the vicinity of the critical point. And I told you already that in the vicinity of the critical point, just like in the equilibrium system, that we get divergences. So for example, the correlation lengths diverge with power laws. And to understand these power laws and to get the exponent, we could in principle naively, if you want to have a system at a critical point, we want to understand the macroscopic behavior, we could naively just say, okay, let's just average over the entire system over large areas in the system and write down a macroscopic theory of these averages. Yeah, but that's not what's working out. That's called mean field theory. That's not working out very well, because in mean field theory, we basically immediately go to the macroscopic scale. At the critical point, we have the self-similarity. Now we zoom in and the system looks the same as before. And because we have the similarity, all length scales are equally important. They all matter. So we need an approach that allows us to go from a microscopic scale, step by step, scale by scale, to the macroscopic scale. And renormalization allows us to do that. We start with a microscopic theory, like our lattice model, and then renormalization. Renormalization allows us to go from the microscopic scale, step by step, to the macroscopic scale. Now, I derive a description on the macroscopic scale. Now, this renormalization has 2 steps. The first step was coarse graining. That's the basic idea. And with this coarse graining, I showed you that you have a lattice system, for example, an Ising model that consists of lattice points. Then this coarse graining step you can think about as, for example, defining blocks of such spins. Think about a magnet or so, and then representing each block by a new variable, by a new effective lattice site or a new effective spin. Now, the second and third steps were the rescaling scaling and renormalization steps. Now that means we need to make sure that when we do this procedure of coarse graining, this essentially makes our system look fuzzy. Yeah, if I do like this with with my glasses, yeah, then everything looks fuzzy, and my eyes are doing coarse graining. Yeah, so if I do that procedure of these blocks, I now have to make sure that the length scale that I get in my new system corresponds to the old length scale, so that we can compare the systems. Yeah, and by this we first rescale lengths so that our new lattice sites have the same lattice spacing as the old lattice sites. And we also need to rescale energies to renormalize the field, so that the new spins have the same magnitude, for example, +1 and -1 as the old spins. Now, if we do that, then we go from a microscopic, this was described by a microscopic, some action here, some action. If we do these steps, we get a new action as prime. And if we do this coarse graining correctly, then we can hope that the new action has the same structure as the old action. That means that the new action has the same terms in it, just with rescaled parameters. And the way this looks then, also I also showed you already this picture, is that if you consider the space of all actions, P1, P2, that is described by some parameters, then our physical epidemic model has some space in this, has some subspace of this space of actions. And somewhere in this subspace is our critical point. Now we renormalize. Now we start with a microscopic critical description, the microscopic critical action. And then we normalize and we ask, where does this renormalization lead to?
Stefan, we are unable to hear your audio. Like, it's a problem with all of us, and everyone's writing in the chat. There's some problem with the audio.
Okay, can you hear me now?
Yes.
So now you can hear me. Now I'm using the MacBook microphone. Okay, so it's always killing the Bluetooth connection for some reason. Okay, I have to. Can you hear me? Okay. But I think it's the, is it correct that the quality is not very good?
No, it's now okay.
It's okay? Okay, let me know if it's not okay, because I'm using this thing that should give you the echo. Let me know if it's not okay. I'm going to try again with the headphones. Okay, so I don't know where I actually stopped. Yeah, can you let me know where you stopped being able to listen to hear me?
You were talking about where the SI model lies, and then you started drawing the subspace, and then we stopped hearing from the when you started drawing the fixed point.
Okay, okay. Yeah, I mean, it's strange that it's working all the time, yeah, and then suddenly it stops working. Okay, so let's see. Okay, so I stopped basically with the critical point of the SI model. Then we renormalized, and this renormalization process leads us to a fixed point. Once we are in this fixed point, the action is always mapped onto itself. Yeah, that means in this fixed point, once we are in this fixed point, or this fixed point describes the macroscopic properties of our system. And then I defined the set of all actions that are also drawn into the same fixed point. And that's called the critical manifold. Critical manifold. Yeah, and this critical manifold, yeah, and then we look at a different action, for example, this one here. And if you look at this different action, let's correspond, for example, to a different epidemic model. Yeah, and this other action also intersects, has a critical point and intersects this critical manifold somewhere. And when we normalize this other microscopic theory, then the action will be drawn into the vicinity of the very same fixed point. That means on the macroscopic level, both models are described by the same theory, by the same action. And that's called universality. That different theories, that different systems that differ on the microscopic scale show the same macroscopic behavior. And
that allows us, for example, you know that from statistical physics, magnets, you can have different ferromagnets of different materials, and they all show the same critical behavior, and we're able to describe all of them, or many of them, with a very simple model that's called the Ising model. And that's because of this universality. On the macroscopic scale, only a few things matter, and many different microscopic theories, microscopic descriptions show the same macroscopic behavior. And the renormalization group allows us to understand why this is the case. So, and this universality is also the reason why we're here looking at such a simple model for an epidemic. An epidemic is something super complex. There's so many variables and parameters. But if we're interested in the critical behavior, then we can show that in this action that we have, if we added more and more processes to it, more and more terms, more and more interactions, that these interactions in many cases are not relevant on the macroscopic scale. And then in the next step, we can take this fixed point and calculate exponents, and we do this by looking into the directions that drive us away from the critical manifold. These are the relevant directions. Yeah, and if we ask how fast the systems, so these are the parameters that experimentalists need to tune in order to bring the system to the critical point. And if we ask how quickly is the renormalization flow driven out of the critical point, orthogonal to the critical manifold, then this describes, then we can derive our exponents from this. The exponents tell us, let's say, how fast the system goes out of the critical manifold once we renormalize. So that's the general idea. Now let's see how this looks in practice. We started already, so another reminder is to the Wilson's renormalization, momentum shell renormalization. The Wilson's idea was that what I showed you on the last slide here with these blocks. The problem with these blocks is that there's no small parameter. You cannot make an epsilon block or something like this. Yeah, so that's a problematic thing, and that's why these blocks, also so-called real space renormalization, is very often doesn't work or is very difficult. So Wilson's idea was to do the renormalization in momentum space. And that's also a reminder, because we had that already last time, what we do in Wilson's momentum shell renormalization is that we take a look at the space of all wave vectors and we integrate out the smallest wave vectors. And so again, as before, there's like two steps, the rescaling, yeah, and renormalization, and the coarse graining. And here in this case, we do the coarse graining by integrating out a tiny shell in momentum space. So we integrate out the fastest wave vectors, which corresponds to the shortest length scales. And then we can formally describe our fields as phi, for example, is the component by the short wavelength plus the component given by the longer wavelength. And we integrate out the slow wave vectors and the fast wave vectors. And then we integrate out these fast wave vectors at each step. Yeah, that means that we define our action on the long, so small wave vectors, so the long wavelengths, as the integral over the entire action, but we only perform this integral over the very high, on this momentum shell, on these very highest wave vectors in the system. Yeah, and if we integrate this out, yeah, then our momentum shell, our momentum space gets smaller and smaller until we arrive at momentum 0, that corresponds for very small values of these Qs, that corresponds to very large length scales, and so therefore the macroscopic behavior. Okay, so let's begin. So we begin by doing the rescaling study. And this lecture is different from the last lectures, but this will probably mostly be a chalkboard lecture. And we'll have to see how this works on an iPad. And so let's see. I hope it's not too confusing. Actually, you can actually do that on an iPad. Okay, so first we do rescaling. And this rescaling, we say that we have to rescale our length scales by some length lambda with a value of lambda that is smaller than 1. If we rescale our length scales, we also have to rescale all other things. Yeah, so our length scale goes like this. So our x and our action. The time also needs to be rescaled. Yeah, it's not independent of space because it connects to space by this dynamic exponent z. Yeah, z was the ratio between the perpendicular and the parallel correlation exponents. So that's not independent of space. We have to rescale this as well. And we don't know what z is, by the way, but that's our goal. And then we have to rescale our fields. Our fields rescale with some exponent chi when we rescale our x and our time this way. And our other field, the phi tilde, rescales in the same way. Phi tilde, lambda, x, lambda, z, t. Yeah? So we don't know what chi is. Now we don't know what z is. But if we rescale the lengths, we have to rescale the other things as well. Yeah, and chi and phi and phi tilde have the same scaling because if we replace one by the other and we switch time in the action, then we get the same action back. So these phi and phi tilde fields are the same thing if we transform the action accordingly. Okay, so now we just plug this into the action. Yeah? With this, we get that as naught. This phi tilde. Then we have these integrals here, dx, dt, phi tilde of xt. And then comes this part, now tau times lambda 2 chi plus d. Where does that come from? I'll show you later. Del t. So we have here one length scale that gives us the d, lambda to the power of d. We have a time scale integral over time that gives us, that cancels out with this one. That is 1 over time, this time, so we don't have anything. And the 2 chi come because we have the chi from the field from the left-hand side, and later the field from the right-hand side. So now we have this part minus d lambda 2 chi plus d plus z minus 2 times, minus, here it's again, this comes from the fields, the two fields, this comes from the so this comes from the integral over space. This comes from the integral over time. And the -2 comes because this was originally a second derivative in space. We had a diffusion term here. So that's how we get this. So minus kappa lambda 2 chi plus d plus z. Phi of x t. So now we just zoomed, we did the rescaling step. Yeah, we just zoomed out. And this already gives us some change of parameters. And we can now call these parameters, give them new names. For example, this one here is now tau prime. This one is d prime. And this one is kappa prime. Yeah, so this was the part of the action that is second order. Now we take the part of the action that has higher orders, phi tilde. And this part is also integral dd x, integral dt, gamma, well, that's just the prefactor, that's the strength of the noise originally, and lambda 3 chi, because now we have 3 fields. We have our 5 fields, phi, are always in third order. 2 chi plus d from the integral over space and plus z from the integral over time. Now come our fields, phi of x t, phi tilde of xt times phi of xt minus phi tilde of xt. Now, so you see that these fields always appear like cubic order, and that's why we get now 3 chi instead of 2 chi. Yeah, so now we have already an equation that updates our parameters by this one step. Yeah, so now we say that for infinitely small coarse graining, that means our momentum shell is very small. So we say that this capital lambda is something like 1 plus L. Yeah. We obtain the first order the following updating scheme. Tau prime is equal to 1 plus, that's of course a Taylor expansion, L times 2 chi plus d times tau. We have kappa prime, next one is d in the list, d prime, 1 plus L, 2 chi plus d plus z minus 2, d. Kappa prime is 1 plus L, 2 chi plus d plus z times kappa, and gamma prime is 1 plus L, 3 chi plus d plus z times gamma. So that's the updating of our parameters based on this rescaling step. Yeah, and this updating of these parameters it's a result of dimensional analysis. Yeah? In principle, you can, if you look at this, you can get this updating here just by looking at the dimensions of things. Yeah? And so this part here was mathematically, so to say, zero effort. But in the second part, the coarse grain part, you have to invest a little bit more thought. So how do we do that? No? So how do we do the coarse grain step? Coarse grain step is difficult because we have to integrate over the momentum shell in this action. And this action has parts that are cubic in the fields that we don't know how to integrate. We know how to perform Gaussian integrals, second order terms in the fields, but we don't know how to integrate third order terms in the field, higher order terms. Yeah, so think about also like statistical physics, 5 to the 4 term. In the 5 to the 4, in the Ginzburg-Landau theory, you have a 5 to the 4 term, and we don't know how to integrate these things. So what we do is what we say. So and I'm only so these calculations are really lengthy. What I'm doing here, I just give you for this coarse graining step. I just give you, so to say, an overview of the steps, but I don't perform the actual integrals. If you're interested in the details, there's a review by Hinrichsen. And this review is about non-equilibrium. What is it? Non-equilibrium phase conditions or some non-equilibrium something. Yeah? And but you immediately find it because there's not so many people who are called Hinrichsen and write reviews with 1,600 citations on non-equilibrium phase conditions. And there you can find in the appendix all of these calculations and how to perform these calculations. So I just give you a glimpse of how this works. Yeah, so the first step is to say, okay, we expand our action to first order. And that's called the cumulant expansion. If we do this cumulant expansion, then we see that our next action, our updated action, is equal to the action in the lower wave vector, so on the larger length set, so inside the momentum shell, so in the core of momentum space, plus the first moment of this interacting action. Yeah, so you see, so plus the average expectation value of this interaction part of the action, evaluated in the momentum shell, and evaluated in the context of the free action that only has the Gaussian term. So that's what we see here. And then there are higher order terms. So this contribution that we get is integral, where the action here, so the definition of this average is like this, that we integrate only over the momentum shell, so the highest momentum we have in the system, and we wait for the average. We wait not by the full action, but by the Gaussian action. Now that's the approximation. Then there are higher order terms that come on top of that. And so what you see here is a little bit what happened here is that we expanded the exponential in this action here by assuming that these interactions are actually weak. Now that we expand the exponential and we have a linear term here in front of that, and if these interactions are weak, then we can make this expansion here. And for today, we truncate it after the first order. And the whole problem reduces to calculate calculating this thing here. Now, we still don't know how to calculate it, but it involves something that is second order in the fields. Yeah, so that might actually be something that we can do. And there's this theorem that helps us to do these things. That's called Wick's theorem. So this theorem tells us that if we have such an average, so for example, this is some product of some fields here, and if we have an average over a product of fields, and if we evaluate this average, or if we calculate this average in the framework of the Gaussian or the second order action, then this complicated thing can be expressed by a sum over all pairwise contractions of these fields. Yeah, that means that we look at all pairs of the things that we have on the left-hand side, put them together into groups of 2, average around them, and then multiply and sum over all possible ways of how you can partition this product here into groups of 2s. Now, so for example, on the bottom, if you have 4 fields or fields evaluated at 4 point in times, so here signified by phi 1, phi 2, phi 3, phi 4, then we just have to look at all possible combinations of how to make groups of 2s out of these 4 fields that we have. Yeah, so that reduces the problem of calculating something that is highly nonlinear to something much more simple. We only have to write down all possible combinations of these pairs called contractions of pairwise contractions here. So these groups of 2s, and just have to sum up all possible ways of how we can do that. Yeah? And each of these things here is now an integral, sorry. There's one thing I forgot, that should have a 0 here. As always in the context of this simplified action. Now, so that reduces the complexity of the problem to something that is only second order in the fields, from something of general order. And what we don't get then is, what we have to pay for is a bookkeeping problem. Because if you can imagine, if this thing on the left-hand side is sufficiently complex, then what you have on the right-hand side involves a lot of different terms. So yet that's a bookkeeping exercise. And because it's a bookkeeping exercise, that's difficult to overview, because you get many, if you have like not 4 terms, but 8 terms, there are many possible ways of how you can make these pairs of 2s. Yeah, and this is why people invented a graphical language of how to represent these terms. And this graphical language in statistical physics or in quantum field theory is called Feynman diagrams. In our case, this graphical language is actually pretty simple. So we also have Feynman diagrams that we place that describe such terms here. But in our case, these diagrams have a real meaning that is connected, or an intuitive meaning that is connected to the time evolution of the system. So first, what the Feynman diagrams say is that if you have something, if you have terms of this structure here, then each of these here, so that also called the propagator that we already had in the action. So these propagators here, these 3 propagators, they all become like a line. Yeah, and this also becomes a line. And once you have things that are integrated over, so for example, you have here integral over the coordinate z. Now the same coordinate appears twice in your term, then you have to connect these things, these legs, in these Feynman diagrams. Yeah, so we won't do that here today. Yeah? So that's a subject of the quantum fields theory lecture. Just to say that there exists this graphical language. Now, in our case, because we're only going to first order, we don't have to deal with that. But I just want to say that these Feynman diagrams that popped up in this, that usually pop up in quantum field theory, they have a very nice intuition in these directed percolation problems. So here, it's actually I copied that from the review of Henriksen. These diagrams, that for example look like this one, this loop here, corresponds actually to trajectories that you have in space, something like this. Yeah, basically what you do is you have your building blocks of your theory. For example, the free propagator. That would just be the Gaussian term, and but you also have these other building blocks that corresponds to higher order terms. And then you just put them together. And these higher order terms, for example, this one here, have a real meaning in this theory, in this framework, because, for example, this one would correspond here to a branching event, or this one would correspond to a coalescing event, where, so one of these, if you look at this space-time plot that we previously had the upside down, then these would correspond to events where such a separate droplets form and then they merge again. So that's how these diagrams are interpreted in the frame of directed percolation. But as I said, that's just a side remark, and we don't actually need that today because what we get is not that complicated. What we do today is that we now proceed with the integration of this of the different parts of our action. So using what we said 2 slides away, 2 slides before, this formula here, so that we expand our action in this way, and Wick's theory. Okay, so let's begin. So this is now the second step, is the coarse graining. Also, so let's say not say coarse graining, integrating out the short length scales on the momentum shell. And we start by looking at the free propagator. And I'll show you now how this looked like. Lots of slides go. So here we have the action and momentum space, and the free propagator is just what is in between. It's the inverse of what is in between the second order part of the action. It's just the same as in quantum field theory, or if you have already quantum field theory or statistical field theory. So it's just the very same thing. So this one is called the inverse of the free propagator. And it's called free propagator because it gives you the propagator. That means how you go from one point in space and time to another point in space and time, using only the free theory without interactions. So this is the free propagator, and this term here is what we have to integrate first. Okay, so the free propagator is G naught of K omega that was just defined by the, okay, we actually use K or Q. K, we use K or Q? Let me just check. K, okay. dk squared, it's just a definition. Minus kappa minus I tau omega. And now, to first order, the propagator is renormalized by following thing. So what we actually have is the inverse of this, so 1 over this. Prime prime is the free propagator after the first step. So where we have already done the rescaling. Omega k plus now, so yeah, first using mathematical extension minus gamma squared over 2, then the integration over this momentum shell, dk prime, d omega prime, then d mod of k over 2 plus kappa prime, omega over 2 plus omega prime times g mod kappa over 2 minus k prime, omega minus over 2 minus omega prime. So now you see we have these two propagators, and these propagators, you see here, that's what we had in the Wick's theorem, is basically phi of k, phi of k prime, these kind of things. So now let's just Wick's theorem, and in the Feynman language, in the language of Feynman diagrams, this is just this. So we have these two arms here, and we integrate over the k's. So there's an integration over k and omega. So they're not independent of each other. So that's why they have a loop. Don't get distracted by these diagrams. It's not so important. It's just for those of you who have already had quantum field theory, just to see the connection. Okay. And now we can write that explicitly. So this first term is k prime prime minus delta d prime prime, k squared plus I tau prime prime omega. Now that's just this on the left-hand side. That's how we define that. It should have the same form as before. That's equal to k prime minus d prime, k squared plus I tau squared minus, and now comes this integral here. And I'm just telling you the solution. Of course, these integrals, the diagrams of everything are just a way of writing things down. But in the end, you have to solve integrals. And you can, if you're interested in how this works, you can look into the appendix of this review of Hinrichsen that I told you. I show you here just the result, because what we actually want to focus on is the renormalization fluid set and not integration techniques. So I just give you the result, L kd. I'll tell you now what this is, omega to the power of d, 2 tau, 1 over omega squared d minus kappa minus omega squared d over 4 omega squared d minus kappa squared k squared plus I tau over 2 omega squared d minus kappa squared omega plus higher order terms. So this KD here is just surface area, a surface area of a d-dimensional sphere. Now, that just comes from the integration. Just you're integrating over a mantle shell, that's what you expect to get some kind of surface of a sphere. But now the important thing is that we now have here different terms. Now I'll just mark them in colors. We have this term. We have the D term, and we have the I tau prime prime double term. And now we have the same term on the right-hand side. So we have the kappa term. That pops up here and here again. We have the D that pops up here and here. So that's a prefactor of this k squared. And we have the tau that we have here and here. And this should have an omega. Okay. Okay, so now we have kappa squared on the left-hand side, and we have terms on the right-hand side that look exactly in structure like the ones on the left-hand side. And now we can compare them one by one, these terms and these two, this one and these two, and get our kappa prime prime, d prime prime, and tau prime prime by comparison to the right-hand side. So I'll just tell you the result. That's the renormalization of the model parameters. So we have tau prime prime is equal to tau prime minus, now there's a little bit of algebra involved. It was just comparing the left and the right hand side of these equations and putting terms together that have the same structure. Kd over 8 omega squared d minus kappa squared. D prime prime is equal to d prime minus gamma squared L kd omega squared d over 16 omega squared d minus kappa squared. And final one is k kappa squared kappa prime prime is equal to kappa prime minus gamma prime L kd over 4 tau omega squared d minus kappa. And for convenience, we define this one here now as A, and we define this one here as B. So now we have the updating scheme, total updating scheme of 3 of the parameters that in principle allows us to link tau prime prime. So after the 2 or the 3 steps of the renormalization group procedure, we update our parameters in this form here. And we still have to plug in the tau prime from previously, from the rescaling step. But there's one parameter missing, and that's the ugly one. Now that's the one that describes our higher order terms. Now, as you can imagine, these integrals of the higher order terms are not that beautiful. Yeah, but I'll just tell you the result, namely that the cubic, so-called vertices, that's just cubic terms in the fields, we normalize as gamma prime, gamma prime, and then we have these diagrams here. This one here, and this one. This one here. Yeah, so you can see that these are interaction terms. That's third order. That's why they have 3 legs. But they're also connected here. Yeah, and but both of them, one of them is just a time reversion of the other one. So both of them have the same value. So I just now tell you the result of this step here. Gamma prime is gamma prime minus L gamma to the power of 3 k d over 2 tau omega squared d minus kappa squared. Yeah, so now we have the updating of all of these parameters. And what we now do is that we go to the limit of, so this is not very convenient, right? Because we have to still to plug in the tau prime and d prime, and then we still don't have anything that we can deal with. Yeah, so we don't know how to deal with these updating schemes. It's much more convenient to have something that gives a differential equation. Yeah, but it's easy for us to derive a differential equation. Namely, we just set the limit in the limit L to 0. Yeah, so that we really just integrate out a tiny bit each step, so that the momentum shell is extremely small. We can write these relations in differential form. Yeah, and I'll just give you the result. Delta L tau is equal to tau times 2 chi plus d minus 2 times a. Now then the a was the thing that we got from the integral in the second step. So obviously I already substituted here the first rescaling step. L d is equal to d 2 chi plus d plus z minus a. And then the kappa is equal to the scale derivative of kappa is 2 chi plus d plus z minus b. And gamma, these interactions, are given by gamma times 3 chi plus d plus z minus 8a. This is now called the renormalization group flow. This is what I showed you at the beginning of the lecture, where I said, okay, so the space of all possible actions, our minimalization brings us, lets us travel through the space of all possible actions. Okay, now that's the renormalization group flow. And now we're in the framework of nonlinear dynamics. And now we have some differential equations that are coupled, and these differential equations we now need to treat with the tools of nonlinear dynamics. Okay, so first we simplify that a little bit. And what we do is when we do the coarse grain, yeah, in space and time, anything that we should get should be independent of the scale of coarse grain because our system is self-similar. Yeah, and so that means we have we have a choice to set the length scale and the time scale to whatever is good for us. Yeah, and I'll tell you what is good for us now. We set the time scale. Set the time scale such that del L tau is 0 and length scale such that del L, what is it, D is equal to 0. Yeah? And then we get two equations from that. Yeah, just by setting the left-hand side to 0, it's 4 minus epsilon, which I will define, plus 2 chi, mu minus 2a is 0, and 2 minus epsilon plus 2 chi plus z minus a is equal to 0. Yeah, and here I set epsilon equal to 4 minus d. Yeah, and with this, I'm left now with two flow equations. One for kappa and one for gamma. Kappa is 2 plus a minus b. Gamma is gamma epsilon over 2 minus 6a. Yeah, so that looks already a little bit nicer. Okay, so the next step, we're almost done with the hard stuff. In the next step, it's not a lecture. The next step, we're interested in the fixed point, because the fixed point determines our macroscopic behavior. Yeah. Okay, so behavior near the fixed point where, by definition of the fixed point, kappa, derivative of kappa and the derivative of gamma are both equal to 0. Yeah? What we then get is the value of a star, that A, our complex term that we had before, at the fixed point takes the value of epsilon over 12, and B takes the value 2 plus epsilon over 12. And now we substitute that into, let me see, this equation here. We substitute into this equation, and we get our first two critical exponents. Chi is -2 plus 7 epsilon divided by 12. And Z is equal to 2 minus epsilon divided by 12. Now, so we have our first two critical exponents. And now, we substitute just this into the proper definition of the fixed point. Now our A's and B's are something complicated. And now we just rewrite it down. Substitute definition of A and B. And what we then get is that kappa star, or a real fixed point, is equal to 4d gamma squared epsilon divided by 24 plus 5 epsilon. So everything I'm doing right now is not complicated mathematics. It's just algebra. Gamma star is 2d24 plus epsilon over 24 plus 5 epsilon. Epsilon tau over kd. Okay, so this is our fixed point. And in the next step, we linearize around our fixed point. Linearize our G flow around fixed point. Remember, in nonlinear dynamics, what we do is we put ourselves into the fixed point. So now we got the fixed point. Now we want to say, is it stable or is it unstable? Will we be pushed out of the fixed point, or will it be sucked in? Is it attractive or not? And the way we do that is we go into the fixed point, and what we said in this dynamical systems lecture is that we then look at the derivative in the 1D system, the derivative of this fixed point. And here, what we do is linearize around the fixed point, and then the derivative in higher dimensions is called Jacobian. That's what we do. It's just an expansion around the value of the fixed point. And what we get is that L in now the vector form kappa gamma is equal to, that's the Jacobian of our flow equation. So 2 minus epsilon over 4, 0, 0, minus epsilon. And then here the distance to the fixed point. Kappa star minus kappa, and gamma star minus gamma. And of course, we have higher orders. So the eigenvalues of this Jacobian, they tell us whether this fixed point is stable or not. So here we're just looking at a nonlinear dynamical system, but we use the same tools. And if you have not just one dimension, but two dimensions, like here, we're now looking at the Jacobian and at the eigenvalues of this Jacobian. We're not looking at the slope in the fixed point as a 1D, a simple case. Now look at the eigenvalues of the Jacobian. This is the Jacobian. Okay, so the eigenvalues determine stability. So we have that 2 minus epsilon over 4 is larger than 0. That means that the fixed point is unstable in the direction of the parameter kappa. Minus epsilon, I'm sorry, that's not a real epsilon here. Epsilon minus epsilon is smaller than 0. That means the fixed point is stable in the gamma direction. And what this means, if you think about our language that we introduced at the beginning of the lecture, is that the parameter kappa drives us away from the critical manifold, and the parameter gamma pulls us, basically pulls us into the critical, into the mineralization group fixed point. So now we're in a position to draw that. So we can have a little diagram. It looks like this. Kappa and gamma. And so here we have our fixed point, and then our flow. Let's see, some lines. Our flow will go into the fixed point along the gamma direction. And out of the fixed point along the kappa direction. Yeah? That means also points on blue line flow into the fixed point. That means we need to tune kappa to reach the fixed point. Yeah? So now we get the final exponents. Yeah? Now with the definition of these exponents are chi, chi was this, at the very beginning, we introduced the chi as how the fields rescale when we change the length scale. Yeah? And by this definition of chi, this is equal to our older definition of these exponents, beta over mu perpendicular. The z was defined as the dynamical critical exponent as mu parallel over mu perpendicular. And kappa is our distance to the critical point, lambda minus lambda c. And that's how we call it when we introduce the problem. Okay, and then we just plug these things in and we get these three exponents. Now, beta is equal to 1 minus epsilon over 6. Mu perpendicular is equal to 1/2 plus epsilon over 60. And mu parallel is equal to 1 plus epsilon over 12. And these are our exponents now that we got from the linearization procedure. So how general are these results, these exponents? We took a simple epidemic model and derived exponents. At the beginning of this lecture, I told you something about universality. That different models or different microscopic theories are described by the same macroscopic behavior. So, and this is something that's not completely understood, but the models that are described by the same critical exponents are said that they belong to the directed percolation universality class. Yeah, and the model belongs to the directed percolation universality class if, that's the so-called directed percolation conjecture, it displays a phase transition. It displays a phase transition between active and an absorbing phase. So this existence of one absorbing point is very important. The second thing is, the absorbing point was when the disease got extinct. The second is order parameter, the order parameter is positive. And the system is a one-dimensional system. Yeah? So the spatial dimension changes as you see from these exponents. The order parameter, I'm telling one. The order parameter is one-dimensional. So you have which is one-dimensional order parameter. The order parameter is scalar, so it's not spatial dimension, of course. Okay. The third one is there's no other bells and whistles. Yeah? So you have no special attributes, no special attributes like spatial heterogeneity. Yeah, so if, for example, your infection rate depends on which lattice side you are on, then these exponents could be different. So what it says is, if these three conditions are fulfilled, you can expect your system to be in the directed percolation universality class and to have the same critical exponents. Now, just before we all go into Christmas, there's now a little final riddle for you. So in the beginning of the lecture, we talked about what is a non-equilibrium system. And the way we define it, and there are different ways to define it. The way we define it, is that we said, okay, the system is in contact with different baths, and these baths are incompatible. So what are the baths in directed percolation or in this epidemic model? Yeah, so really, normally if anybody was in the room now, we would try to solve that together. But as you're all sitting in front of your computer and maybe watching Netflix in parallel or so, so I'll give you the answer. So what is actually here the bath? Directed percolation. So it's actually quite difficult to see that. What are the heat baths? What are the baths? What drives directed percolation out of equilibrium? It's the absorbing point. That you have a point where you can go in, but you can never go out. And when you're in that point, then you're clearly not in equilibrium because there are no thermal fluctuations. Now in reality, and this is an approximation, that you have an absorbing state. In reality, you can get out of the absorbing point. You just have to wait a few 100 million years for the virus, one that had gone extinct, to come back by evolution. That takes a long time, but this process exists. But we say in this theory that this probability or this rate with which you get out of this point, out of the absorbing state, is exactly equal to 0. Yeah, that's the tiny thing that we do. And what this means is that the system is coupled to 2 heat baths. And these heat baths are incompatible. There's one heat bath that has a temperature 0, and the other heat bath that has a temperature that is larger than 0, that causes really some fluctuations. Now, what are these heat baths coupled to? Yeah, the funny thing is that these heat baths are coupled to time. Yeah? So in one time direction, dt smaller than 0, yeah, you have 0 temperature in the vicinity of the absorbing state. And in the other direction, dt larger than 0, you have a finite temperature. Yeah, and these 2 heat baths coupled to different time directions makes the system allowed to go into the absorbing state, but never leave it. Yeah, that's this asymmetry that of these 2 incompatible baths that makes this one of the hallmark non-equilibrium systems in non-equilibrium physics. And what I showed you actually here, this universality class is extremely powerful. There's a lot of models that have nothing to do with epidemics that fall into this universality class. And so it's one of the paradigmatic models of non-equilibrium statistical physics. Okay, so that was quite a tough lecture. Yeah, so also for me, I'm quite exhausted. And what I would say is that you will have a great Christmas. And after the new year, on January 5th, I think, so our next lecture will do something completely different. We have a look at some real data, and we'll get into data science and see what actually to do with data, if this data is really, really large. And how actually to see these things that we've studied in the last lectures, in the last 3 months, how to actually see that in data. Now, that's not very trivial. If somebody comes up to you with 10 terabytes of data, then you can't just start MATLAB and start fishing around. And you need special tools from data science that allow you to extract such features from data that can have 100 millions of dimensions. That's what we do right after Christmas on January the 5th. And once we've done that, we'll also have some guest lectures done by real experts in these fields. And once we've learned like the fundamentals of data science, we'll put that all together and look into some actual research data and see how we can use these tools from field theory, visualization, data science to actually dig into some current experimental data. Okay, so then Merry Christmas, everyone, if you celebrate that, and see you all next year. Okay, bye. Now I'll stay around if there are any questions.